Hello everyone, this is Boopathy presenting you a research paper which is Dynamo, Amazon's highly available key value store. Let's move on. The versatility of Amazon, as you all know, Amazon is worldwide. Its products, its services. You can see a list of products, the App Store, AWS, whatever it is, and the services. It's online shopping, as you all know, the Amazon.com website which sells crores and crores of products online. And the cloud computing, Amazon has a cloud which in the name of AWS, which gives platform as a service, software as a service, infrastructure as a service. So to have an insight of Amazon's cloud, you can have an AWS account. It is aws.amazon.com/console. You will have the console window where you will have a list of infrastructure provided from Amazon. You can have a list. Let me grab it to you. So this is the Amazon's AWS console, which has a lot of modules. EC2 is a server instance in a cloud. Uh, you can see S3, which is the storage, the cloud storage for Amazon, and you can see DynamoDB here. We are going to look brief of DynamoDB in our upcoming slides. Um, yeah, there's a lot of things in Amazon where there's a lot of companies getting services from Amazon online, so that they don't need to set up any uh, data center software, whatever is it, the infrastructure. Uh, they can get it from Amazon, so that just with a user ID, I mean a login, you can store data, retrieve data, do whatever a world-class company does. So there is Amazon Web Services, and yes, so content distribution. Content distribution is actually again the websites, its contents is stored in Amazon servers online. So you don't need to have any servers for your website. The content is stored with Amazon secured. Uh, so there's content distribution. We have what is a data center. Uh, an Amazon data center, especially which is having hundreds of services, thousands of commodity missions, millions of customers at peak times. Yes, millions. And yeah, what is the CEO telling? The CEO says, Amazon CEO, his name is Jeff Bezos. His idea is, our job is to invent new options that nobody's ever thought of before and see if customers like them. Yes, ultimately it is customer oriented. Let's move on. So our topic under consideration is Dynamo. What is Dynamo aiming at? So it's reliability ultimately, which is scalability, not even a slight outage, strong customer trust, high availability, load balancing, failure tolerance, and yes, the cap properties. So scalability is how ready the resources are when the number of users increase or decrease rapidly. Not even slight outage, uh, no system crashes, and yes, of course, strong customer trust, the high availability, of course, which Amazon is aiming. Um, the cap properties, it fulfills the availability and load balancing, but it compromises with consistency, which we see it in the future slides. The failure tolerance, of course. So on the whole, it's the so-called always on experience. This is a famous saying: performance plus reliability plus efficiency is money. So that is what Amazon formula. So let's move on. Here's the cap theorem. The cap theorem states that In a distributed database system, you can only have at most two of the following three characteristics. It is not we can have, it is the possibility that we have. It is consistency, availability, partitioning. Only two of these. What is consistency? All nodes in the cluster see exactly the same data at any point in time. So, uh, what is availability? So, failure of a node does not render the database inoperative. That means even the node crashes, the other node supports, and there is availability all time. Partition tolerance is like nodes can still function when communication with other groups of node is lost. So the network partitioning, the network traffic is again playing an important role. So Dynamo compromises with consistency and is having high availability and network partitioning tolerance. These are the other uh, uh, principles that follow that aim in availability and network partitioning but slightly compromise with consistency. Let's move on. So these are the things we are going to see, the background, how Dynamo evolved, and the system architecture, how is it implemented, so what are the observations and learning, and finally the conclusion. So the background, system assumptions and requirements. So we assume a system um, which is a query model, like simple read and write operations to data item is uniquely identified by a key. Of course, we know the asset properties, so we are assuming a system that uh, has good asset properties. Of course, efficiency, um, latency requirements, which are in general measured at the 99.9th percentile of the distribution. So we don't prefer latencies, so it should be highly efficient. So our other assumptions are like the environment is assumed to be non-hostile, and we don't consider any security-related requirements and like authentication, authorization, etc. So we build a distributed storage system which is going to be scalable, um, a simple key value, and highly available, which is guaranteeing service level agreements. So moving on. This is the service level agreement. Application can deliver its functionality in a bounded time. Means uh, whatever functionality is expected, it delivers in a bounded time. For example, if a system is with at a peak load of 500 requests per second, it still responses within 300 milliseconds for 99.9% of its requests. So that's the way it goes. Moving on. So these are the design considerations. So as we spoke earlier, sacrificing consistency for availability, we get a lot of benefits. So conflict resolution is executed during read instead of write. That is always writable. These are the other principles that we need to consider. Yes. So this is going to be the system architecture, which is a list of divisions: system interface, partitioning algorithm, replication, data versioning, execution of get and put operations. Yes, that's more important. And the handling failures, handling permanent failures, membership and failure detection, adding and removing nodes. We will see more on that. So yeah, the system interface. So as we all know, it stores objects associated with a key through two operations, the get and put. So the get operation locates the objects associated with the key, and the put operation determines where the replicas of the object should be placed, like it is placing the object associated with the key. Um, so the context encodes system metadata about the object that is opaque to the caller and includes information such as the version of the object. So as you see, context info is stored with the object to verify the validity of the put request, which is 128-bit key, and object is treated as a blob. So this is a summary of techniques we used in Dynamo and their advantages. This slide is very important because these are the techniques and the problem, the techniques and the advantages. So this slide is most important. So as you see, partitioning, we use the technique consistent hashing, and the advantages scalability, incremental scalability. For high availability, we use vector clocks, which is we study in our classes. The Lamport's logical idea of vector clocks. Yeah, logical clocks for read consistency. And how about handling failures? The sloppy quorum and the hinted handoff, which we are about to see in our upcoming slides. Yes, so membership and failure detection, which is based on gossip-based member protocol and failure detection. Yes, so moving on, this is the partitioning algorithm, which is consistent hashing. So consistent hashing is the output range of a hash function is treated as a fixed circular space that is a ring based, which we also studied in our classes. A ring based algorithm, which use virtual nodes. So each node can be responsible for more than one virtual node. It is k by n assignments when adding and deleting nodes. So yes, so advantages of virtual nodes is that it is easy to add and delete nodes. When a node becomes unavailable, the load handled by this node is spread across the remaining nodes, so that the load is evenly distributed. And when a node becomes available again, it is put in the right place, and the other loads from the nodes is it is assigned some load, so that load is again evenly distributed. Um, the number of virtual nodes that a node is responsible can be decided based on its capacity, accounting for heterogeneity in physical infrastructure. You can see the ring-based nodes here, and we will discuss about this in future slides. Moving on, it is here is an example of partitioning algorithm with the consistent hashing. This is a small animation which you can look at it, and I'll explain it later. So the consistent hashing is actually can take it here. So um, DynamoDB employs consistent hashing, which is normally in a traditional hash tables. Any change in the array size will affect all keys to be remapped. But in consistent hashing, if you use the same hash table, you know, k by n keys need to be remapped on an average. We don't need to remap everything. It is just k by n, where k is the number of keys and n is the number of slots. So this is one advantage of consistent hashing. The animation which you saw is a small example of consistent hashing, which is 128 bits key values. Um, so uh, this is it. And sloppy quorum and hinted handoff is also the other techniques where so um, DynamoDB would experience reduced durability and availability in the traditional form of quorum approach. Um, in order to overcome this, it uses a sloppy quorum where all read and write operations are performed on the first n healthy nodes. So the operations are performed at the first n healthy nodes from the preference list. This may not be the first n nodes encountered by traversing. It is the first n healthy nodes from the preference list. Um, if we consider the above figure, if A is temporarily not reachable during a write operation, then the replica that would have lived on A will be sent to D to maintain the desired availability. So if a node is not reachable, its replica is sent to some other node. Uh, so so the replica D will be sent, will have a hint in the metadata. The data which is sent, it has a hint. The hinted replica are stored in a separate local database, which is scanned periodically to detect again if A has recovered. um, so D will send the replica to A as soon as it detects A is recovered, and may delete the objects from its local store without decreasing the total number of replicas. So using hinted handoff, DynamoDB ensures read and write are successful even during temporary node or network failures. So the hinted DB comes in act when there is a temporary failure of nodes, whereas a Merkle tree comes in act when there is permanent failures. So for handling a permanent failure, Merkle tree is used, which has been explained detailed in here in this reference. So you can have a watch later. This is all about hinted handoff, sloppy quorum, and Merkle tree, the consistent hashing, which are um, the techniques, which are the techniques. Let me go back to show you the table. So which are the techniques for each problems of partitioning, the availability, the handling failures, etc. So these are the important techniques. So let me come again. So consistent hashing is using consistent hashing technique, we can overcome the disadvantage of remapping all keys again. um, um, we need to remap just k by n keys. Sloppy quorum is maintaining all read and writes, whereas the hinted handoff sends a hinted replica from a failed node to another node, which in turn keeps checking if the node is active again, and it again retrieves the data in the same node. It erases the data from its local node. So this is hinted handoff. uh, yeah, so moving on, replication and data versioning. Yes, the replication is done at n hosts. We have a preference list which has a list of nodes that is responsible for storing a particular key. So this replication of data is done at n hosts from the preference list. Dynamo provides eventual consistency, which means allows update to the propagated to all replica asynchronously. The put and get operations locates and uh, places the keys in respective places. The challenge is that an object having distinct version subhistories, which the system will need to reconcile in the future. So here comes the solution for this. Is the solution is the vector clocks. As we learned in our classes, it's the vector clock concepts of time stamping. We will see in the later slides. This is vector clock time stamping. So there are three events or processes which has a lot of events in each process. So so the events in the blue region are the cause leading to the event before. This is the event before, and this area is the effects of event before. So you can see the timestamps. These are logical, and this has solved a lot of issues in ordering events, so that everything goes well in a distributed system without compromising the issues in distributed systems, without violating the casualty, to be specific. Moving on. Yeah, this is a slide for hinted handoff. So when the node A is inactive, a replica with a hint is sent to node D, which the metadata which contains the hints. So through that, node D keeps checking whenever A is active again, so that as soon as it gets active, it sends the data to A again and erases from its node. So which is again like always writable. So there should not be any outages in writing operations, which is ensured in this hinted handoff. Yeah, this is the sloppy quorum, where R is the minimum number of nodes that must participate in a successful read. W is the minimum number of nodes that must participate in a successful write operation, and the setting should be like R plus W is greater than N, which is a quorum-like system. So again, the latency is minimum, which is ensured in this, and um, R and W are usually configured to be less than N, which is very important to provide better latency. The get and put operations, as we discussed, is mentioned here. Um, um, yeah, the coordinator writes a new version of vector clock locally and forwards it to the n highest ranked reachable nodes. If W minus one more write succeeds, the write is considered to be successful. Moving on, this is implementation. So each storage node has three main software components. The first one is request coordination, membership and failure detection, local persistence engine. So local persistence engine components allow different storage engines like the below mentioned. Um, Everything is implemented in Java. Moving on, these are the membership and failure detections. So as discussed, it is a ring membership, which is like which uses background gossip to build one minus hop through the I'm sorry, it is one hop through the distributed hash table. These hops are based on algorithms, which you can find it online. So the managed system administrator explicitly adds and removes nodes, which is called a well-managed system. So membership is maintained well when nodes are added and removed by itself. That is not a well-managed system. So these are the passive failure detection. So it uses a message for detection to see if a node is failed or alive. So for example, if A detects B as failed if and only if it does not respond to a message. Periodically, A periodically checks if B is alive again. So as soon as it is alive, it shares its work and balances load. So in the absence of client's request, A does not need to know if B is alive. So permanent node additions and removal are explicit. Moving on, this is a slide where we uh, demonstrate adding and removing nodes. So a new node X added to system. Um, yeah, X is assigned key ranges with respect to its virtual servers. For each key range, it transfers the data items. So this is one good image of adding and removing a node. So when a node X is added, the nodes of the previous and the successor nodes are remapped. The data again is remapped so that its data is shared and the load is spread equally. Whenever there is an inactive node, node is it keeps checking and finally it is removed, and the node's work is shared between the other nodes. And when there is a new node, the new node takes responsibility of the previous nodes and it shares the load of the other nodes. So it is the vice versa. Moving on, these are the insights and observations from our learning. This is a diagram which gives you the latencies. So it is a nice picture. This is DynamoDB's high velocity scaling. These are the applications that use it. Yeah, so this is one nice slide where you can see a list of applications. Yeah, moving on. So, and finally, Amazon's DB aims in these important attributes. So let me conclude with scalability, simplicity, like just get input maps well to Amazon's workload, and flexibility, which is apps can set NRW to match their needs. Inflexibility is like app have to set NRW to match their needs. Apps may have to do their own conflict resolution. So, on the whole, Dynamo has been successful in handling server failures, data center failures, network partitioning, of course, following the CAP theorem, slightly compromising on the consistency, and having strong availability and network partitioning. Uh, Thanks a lot. Happy scaling. Thank you.